Building lighter, better batteries. Some big progress from researchers in Sweden. Welcome back to Techstination. I'm Fred Fishkin. Joining us from Chalmers University of Technology in Sweden is Professor Leif Asp. Thank you for taking the time with us.
Thank you for having me. It's great to meet you.
Well, you and your team of researchers there have announced a step forward in building a battery made of carbon fiber composite. You've been working on this for years. Tell us about the progress that you're announcing here.
Yeah, so we have been able to now utilize carbon fibers in both electrodes, both the anode and the cathode, as you usually say, but we talk about the negative and the positive electrode. We have since years used carbon fibers in the negative electrode as host for lithium and reinforcement and electron conductors, whereas we have not been able to get the working cathode in the same way. But now we have been able to coat carbon fibers with the lithium iron phosphate as an active materials. We have the carbon fibers as reinforcement and current collectors and the scaffold for the LFP, and then we make a full cell with that, so we can actually get a very high modulus carbon fiber composite battery, and also with reasonable energy density.
So tell us the significance of that. What does that mean in terms of the progress here and the advantages? Why carbon fiber?
Yeah, so the reason for using carbon fibers is that they lend themselves to serve both purposes: to store energy as a electrode in the battery, and to carry load as a reinforcement. So you think about it. If you have a car today, for instance, if you think about the long-term application of these, you actually have batteries, and you need to have additional batteries to get reasonable range because of the weight of the car and the batteries. So the batteries provide additional weight, like a structural parasite. But here you could actually, by replacing the monofunctional battery and the monofunctional structural component with a material that can play both roles, you can actually reduce the amount of material and the mass in the car significantly. So that would be the potential of having a massless energy storage by having these multifunctional materials, getting the storing capability for free, so to say.
How much lighter could carbon fiber batteries be than what we're accustomed to today?
It depends on the application. This is the million-dollar question I always get if I speak to industry. It's about the application. So you need to know what you want to replace. If you want to replace a very stiff aircraft wing structure, for instance, then of course you will not be able to make much weight reductions on the structural part. But if you want to replace an steel roof, for instance, for a car with these lightweight materials, then you can expect to get significant weight reductions. And colleagues at KTH, means they looked at the laptop computer and they see potential weight reductions of about 50%. So I think for a car maybe you can expect less, but I think they also did a roof structure of a car and they could see about 20%. So these are depending on the use case and what you want, what monofunction systems you replace.
Those are very significant numbers, the reductions. I understand, and I think you started to explain a little bit, that these have somewhat lower density carbon fiber batteries than other batteries on the market today. But the lower weight means you can more than compensate for that.
Yeah, so I wouldn't be so sure about the density of the structured battery versus the conventional battery. But what I know is that the conventional battery cannot carry mechanical load, and by having this load carrying capability, you can actually replace and invoke the energy storing capability in the structure. So then suddenly you can take mechanical loads, and then you can say that you can have a battery with a composite with maybe a density of 1.8 kilograms per liter, and suddenly have the energy storing capability for free. So that can be handled within that material with that mass.
And as you indicated a few minutes ago, we're not just talking about cars, although that's obviously a huge application here, electric vehicles, but for other battery run devices too. You mentioned
Yeah,
laptops and phones, for instance.
yeah. I think the low power applications are much easier to reach. We are struggling with the power at the moment, so we need to find the approaches to increase power so we can take out the energies quicker. And then, of course, if you look for propulsion, that is needed. But for low power applications like laptops and telephones, they will lend themselves much better to this material to begin with. But obviously, the potential benefits if one can go for propulsion, even in support uh, cars and aviation with electrification, and I guess more imminent can be the 12-volt system in a car or the 28-volt system in an aircraft. But uh, the power needed is something that we work on heavily now to provide.
Where are you in the process of bringing this to market?
So we have started a spin-out company called Synonis AB, and that came in place a year ago, approximately a year ago, and the CEO is in place since May. So I think that if the executive people at the company can identify early adopters, we can get going in the company quite soon. So that we are in a situation, I guess, or he is in a situation where he wants to capitalize this and to start with business development around these materials. But most certainly something that is requiring less the low power applications that can be made imminently, I would say.
And of course, your research is continuing. What are some of the biggest hurdles that you're still facing here?
Yeah, so we're looking a lot on modeling. So I think that we're trying to have models that are multi-physics and multi-scale that allows us to design these batteries better. We have a big team working on that. And as I said, we are trying now to find ways to increase power by reducing distance between electrodes, by perhaps changing something with the electrolytes that we have, trying to find better ways to apply the lithium iron phosphate on the carbon fiber positive electrodes. So we're trying to find the means to boost the energy. We have also some other stuff going, but I will not talk too much about that. But it's mainly focusing on power.
Tell me a bit about the economics here. Will the costs be comparable to today's batteries, or what? I know that it's very hard to say sometimes until you reach mass production, but what are your thoughts?
My thoughts are that it most likely, if you compare to the carbon fiber composite rather than the battery, I would say that the prices would be quite similar when it comes to materials costs. So we have the carbon fibers, which are the costly part of a carbon fiber composite. So you can expect them to be around, I think, about between 30 and 50 US dollars per kilogram to get those. So that would be pretty much on par with what you have in the structure you want to replace. Then, of course, you need to allow for this process and to make these positive electrodes, which will come at a cost. But the manufacturing technique is identical to the one we use for carbon fiber composites manufacturing in some applications today. So I think they will come out pretty much on par with commercially available carbon fiber composites. But then, of course, you need to connect these. When you build the structure, you need to find a way to connect these. And I guess that the assembly situation will be more complicated than for conventional composites. It's hard to say, but I would say from a material perspective, not too expensive, similar to composites, and from a handling situation, I guess that we will be requiring type of connectivity and battery management that you have for conventional batteries. So it's going to most likely be compatible, but it's hard to say. It depends on what you want to replace. If you want to again replace a steel roof for a car, that comes at 30 cents per kilogram or something. That material. So it's of course depending on the situation. Again, the business case it has to be evaluated by the individual who has a need for this technology.
Are you seeing much interest? What can you tell
Yeah,
us?
Yeah. So over the years, we have had always interest, of course. We work quite closely with Airbus over the years and with Volvo Cars and others. So there is a huge interest, but the investments, I believe, are quite high as well. Then, if you want to pursue this, so they are keen to meet, and we have been making demonstrators, and they explore the technology and they support us with in collaborative research. But I guess it's a bit now about to find the really good start application. So I guess that industries may see this and reach out to us with ideas that they may have, and that's welcome, of course. We have had industries from space to drones to cars to handheld tools, quite a variety of people being very interested in the technology for electrified systems.
There is a lot of research being done all around the world, I suppose, on batteries today.
Yeah, it picked up over the years. We started in 2007, and in that at that time it was only the U.S. Army Research Labs starting it, and they gave up quite soon. And the people at the Imperial College in London, they started working on supercaps, superstructure supercaps, and we started working on batteries then. And for the first years, it was not many teams there, but now it's quite a lot of people in the US, in Europe, and in China, and Singapore, Australia. So you can see more than a couple of hundred papers per year in this direction now. So it's actually taking off
Exciting.
dramatically.
So where do you believe that the work you're doing there fits into that overall picture when you turn
I
in
think
terms of
we have,
importance,
since we
perhaps?
have quite a few years head start to others, we have come the furthest. But of course, there are other approaches than using carbon fibers. I'm thinking just going for a solid state battery would actually invoke quite a few of these issues where the electrodes swell when you're charged, and you get internal stresses. So I guess that just having a solid state battery in some sense will be structural. Then it will be quite a variety of materials that you can use, from the low end when it comes to mechanical properties and high end when it comes to electrochemical properties. So the design window that you can expect to see from structural batteries can be vast, I would say.
Very exciting. Is there a place that people can go to get more information about the work you and the team are doing?
Yeah, so we have yeah, yeah. I wonder where we have. There's a Wikipedia page. There's also a nice page at the Imperial College London where they have gathered work that we've done together with them over the last year. So if you look for structural power composites at the Imperial College London website, you will find all the papers practically that we have done. They've been uploading them and putting, I think, even presentations we have given over the years that have been recorded and made them available. So that's also available, I think, and also everything we publish is open access. So if you find a paper by us, you can go and download it. It's free of charge.
Well, terrific, and congratulations on the work and the advancements. We look forward to what's to come. Professor Leif Asp, thank you so much for spending time with us.
And thanks for having me. It was great speaking to you.